there has been an amazing discovery in the world of physics. For decades, physics has been divided by a fundamental problem. On one side, we have quantum physics, explaining 3 of nature's 4 forces with remarkable precision. On the other side stands Einstein's theory of general relativity, our best description of gravity. The problem? These 2 frameworks speak completely different scientific languages. But now, researchers from Aalto University may have found the translator we've been looking for, potentially bringing us one step closer to physics' ultimate goal, a unified theory of everything. Imagine you're writing the rulebook for how the universe works. 3 forces, electromagnetism, the strong force, and the weak force, all fit neatly into the quantum physics chapter. They work with particles, fields, and discrete packages of energy. But gravity? Gravity demands its own chapter entirely. While quantum physics sees the world as jumpy and discrete, Einstein's gravity describes smooth curves in the fabric of space-time itself. When physicists try to combine these views mathematically, they get impossible answers, literally infinite results that make no physical sense. That's where Mikko Partanen and Jukka Tulkki from Aalto University come in. Their groundbreaking approach places gravity within what's called a gauge theory, the same mathematical framework already used to describe the other fundamental forces. Their solution? An 8-dimensional mathematical space. Now don't worry, we still live in our familiar 3 dimensions plus time. Those extra 4 dimensions exist purely in the math, allowing the equations to behave properly without breaking what we already know works. By choosing a symmetry that mirrors the standard model of particle physics, they've found a way to make gravity play by the same rules as the other forces. In this framework, it's energy, not just mass alone, that becomes the charge that gravity responds to. What makes this approach promising is how it handles those pesky infinities. Using a technique called renormalization, the researchers believe they can systematically control these infinite results, turning them into measurable constants instead of mathematical disasters. If successful, this would let physicists compute reliable probabilities for extreme cosmic events where gravity and quantum effects collide, like the edges of black holes or the first moments after the Big Bang. The researchers openly admit their work isn't finished. The theory still needs to prove it can handle every level of calculation, and independent teams will need to test whether it predicts subtle effects that future experiments can verify. But the implications are profound. A working quantum gravity theory could finally explain whether singularities truly exist inside black holes. It might shed light on why matter dominates over antimatter in our universe, and it would unite all fundamental forces under a single mathematical framework, bringing us closer than ever to understanding the deepest rules that govern reality. As Partanen himself put it, like quantum mechanics and the theory of relativity before it, we hope our theory will open countless avenues for scientists to explore. The universe speaks a complex language. For the first time, we might be getting closer to understanding its complete vocabulary. If you found this fascinating, hit that like button and subscribe for more cutting-edge science. And for more on this story, find a link to the article on Earth.com in the description.